This structure here is the, before I begin, I'd like to thank the client, which was the Mississippi Department of Transportation. I'd like to thank our sub-consultant, KPFF Consulting Engineers, especially Adrian Copo and Chris Liegos. They helped us with the cable testing. Anderson Crane and Bridge Technologies provided all of our mechanical equipment. Traffic Control Products Incorporated kept us very safe on the roads, and Dean Pereira and Company, our contractor, did a great job in removing all the cables. Just some structure facts here. This is one very beautiful bridge. It's just such a great cable stay structure. It opened in August of 2010. You know, at the time, it was one of the fourth largest cable stay bridges in North America. And, you know, one thing I learned working on this project is there's only about 50 cable stay bridges, you know, on the highway systems here in America. We have a lot more pedestrian cable stay bridges around, but I didn't realize that we had less than 50. The total length of this bridge, you know, over its 84 spans is just under 14,000 feet. So it's a long structure, and there's a lot of parts to this thing. With its 3 signature cable stay spans, the main span over the Mississippi River there is about just under 1,400 feet. The towers from the top of the deck are about 310 feet, and then the whole structure, the deck and the main span there is about just over 100 feet off the river. So when you're on the top of the towers there, you're a good 400 feet above the river, and you can see for miles there in Mississippi. And so it's absolutely gorgeous. The scope of our services here was to perform a full routine element level structure inspection with all the new NBEs and defect coding, fracture critical inspection of all the edge girders and the floor systems in the main spans, in-depth inspection of all the substructure units and main river span piers and towers, in-depth inspection of the cables and all the anti-vandalism pipes, all the anchorage connections to the edge girders. We looked at all the, you know, we took all the caps off. You know, we did a whole gamut of things on this bridge here. We also did vibration-induced force measurements of all the cables, and that's where KPFF came in and did a really bang-up job there. We also had to disassemble 10% of the anchorages in the tower and down at the deck and do non-destructive testing on them. We also set permanent anchors on the deck to look for long-term creep and movement of the structure. We also did a hydrographic survey while we were out there, so we had a dive boat and this and that, and we also had to provide the written detailed report, which within 30 days of the end of the inspection, which was a very tight schedule for us to meet because it was a very large job. This job here was the single largest job I'd worked on. You know, we've worked on statewide contracts or this or that had larger fees or people, but you know, it was the largest single coordination project that I've ever put together. We had over 21 team members from 5 different offices from Stantec that we had to basically you know, get out onto this job. And we had to coordinate with the KPFF staff, the Dean Pereira, the contractor, all the equipment providers, all the traffic control, the dive boat, all the state patrol, the Coast Guard. And then we had to get all of our gear together. You know, we brought over 11,000 feet of rope out to do this job and thousands of pounds of gear to provide this. We had to basically drive 2 big F-150s with all the gear down to do this job. It was quite an undertaking. We knew right up front that we had to identify, you know, the critical path, and we really needed to prepare for the worst case on this bridge. And so before we even began, the first thing I said is, we're getting 2 snoopers out there, you know, because everyone knows what happens to mechanical equipment. It breaks down, and it did break down. Basically everything broke down at one point. We had to make contingency plans, you know, reserve extra equipment, you know, make sure that we had plans that if we couldn't, you know, be working over the water because if the safety broke boat, then what could the rest of the team do? I mean, anyone that knows that's been out on site, if you've got 21 people standing there and something goes wrong, Well, all of a sudden, equipment breaks down. What do? They turn and look at you, and they're like, "Now what?" And you got, I mean, that's a lot of time. That's every hour that ticks by that you don't have people working. That's 21 hours off of the cost. And we wanted to make this job fast and efficient and economical for the client. One of the big things that saved us, and this is nothing new, but it really was a lesson learned for us and really enforced it, is all the previous inspections were done with hand notes. And they were done with hand notes before all the new NBEs. So we spent a lot of time, actually the entire 8 weeks, we had multiple people entering all of the historic notes into these new database with drop-down menus and pick lists, and we quantified all the defects before we went out there and put them all into the new, their new elements. And it really helped us speed up the report at the end. It took us longer to mobilize for this job than it did to basically perform the job and write the report. So that tells you how much effort that went into doing this job. But it saved lots of times. We worked with tablets out on site, and it just worked great. And also, what was one good benefit is now, going forward, all this data, we gave it all electronically to the client, and so now it'll just make the next consultant that does the job much easier for their preparation. What we learned during the testing is that if you're an owner of a cable stay bridge or you're designing a cable stay bridge, you need to have very detailed records of the stressing of the cables and right after construction. Okay. Basically, they had, VSL actually did the work on this bridge, and they kept very detailed records of the stressing of the cables. But the problem was that some of these cables, they're individually, they're multi strand cables. There's anywhere from 28 to 64 strands in each one of these cables. They had stressing records on each individual cable, or strand inside the cable. And so we tried to add up, or excuse me, KPFF tried to add up the force in each one of the strands and then divide it by the total, average it over the number of strands in each cable to come up with a force, but it just didn't work very well. And so our design loads, after we got done with the testing, the design loads, we just weren't hitting it on the mark. They came out anywhere from 25 to 40% different. And what we realized is that all of the records that were taken, the wearing surface, there's an 1.5 inch sacrificial wearing surface that was put on this bridge after the construction. So that wasn't included in any of the stressing records. And also all of the concrete parapets weren't included. And so that's a lot of dead load over, a 2,600 main span structure here. So if you want to, record, or excuse me, if you want to compare the tension in these cables year after year and over the life of a 100-year lifespan bridge like this, you really need to do the testing that you're going to use for the remainder of the life right after the bridge is constructed. And so that is what we found. Now, there was a lot of reasons why the forces didn't match up. Okay, basically the temperature at the time that they install the cables can affect the results. Small differences in the assumed cable lengths will affect the results. I mean, think of these cables as big guitar strings, and at different frets on the guitar strings. As you lessen the cable or lessen the length, the frequencies get higher. And as the frequencies get higher, or you have a shorter cable, it gets harder to validate the data. And so basically, this is what we found. And so without having an apples-to-apples comparison of a vibration-induced force measurement right after construction by doing the vibration force measurements after, we basically just created the baseline now. But the DOT, MDOT really wanted to know kind of now what the differences were between construction, and we really couldn't tell them. But if we do this again in 5 years or 10 years, we really have a good baseline at this time. These pictures here is a picture. We had a 180-foot man lift out there that the contractor was using to loosen up the wind ties. We also had another 80-foot man lift out there that was helping with the vibration-induced testing. The picture here on the left, or excuse me, the right, is the accelerometer that KPFF was using to get the wave frequencies from the cable. And they were using after they got the frequencies, they used the fast Fourier transform analysis. Basically, if you can induce a frequency in the cable and you know the cable properties, you can back into a tensile force within the cable. They did a really good job, Chris Gallegos, doing all his UT testing and all the testing out there. We also did ultrasonic testing of 10% of the anchorages. So we took the caps off, and they prepared the ends of all the cables. And I really wasn't aware that you could shoot, that ultrasound would be too effective shooting it up the cables, or each individual strand. But apparently, the sound goes anywhere from 10 to 12 feet up the cable. And they're looking there in the anchorages to see if there's any problems with when they stressed it, or when it's over the life of whether any of the strands had broken. We didn't find any problems with the cables really, and the structure's in really good shape. One thing that we did find is, I forgot to mention on the last slide, is that you may not need to do an in-depth inspection of these cables every time. It took 8 of us, basically 2 weeks to rappel 112 cables, all right, and with 11,000 feet of rope. That's a lot of man hours and time. Our recommendation is to maybe do this now every, 3rd inspection or 4th inspection, so maybe every 6 years or 8 years. And then if you want to do interim inspections, maybe just rappel the top cable and then rappel down to look at the wind ties on these structures. But rappelling every single cable is probably not necessary. Above the level of the deck, we really didn't find too much, right outside of the splash zone. So within about 30 feet off the deck, where a truck could hit it or something like that, or debris could fly off a vehicle and impact the sheathing, we really didn't find too much. We found some construction defects where the cable was scraped or dinged or this or that. And as a couple presentations earlier were saying, you may want to check those areas where the cable's been scraped or gouges, because the thermal expansion of the pipe, the polyethylene pipe there, or HDPE pipe, it can fatigue those gouge areas and crack the pipe. So if you have any large gouges, you may want to check those, but you probably don't need to do a hands-on inspection of every single cable. This is just a typical photo of the wind tie here. We did find that some of the elastomer material that's between the wind tie and the cable was kind of slipping out in some areas. There was some loose bolts on these wind ties. But really, when we had the contractor go out there and do the testing, they didn't need to remove the actual clamp and tie. They just loosened the cable up just enough to induce the force in the cable, or excuse me, a vibration in the cable to be able to take the measurements that they needed and back into a force. This is just a general lesson that we learned the hard way. This really has nothing to do with the testing of the cables. We knew that there was a critical angle when we were rappelling the cables. All right, and basically we found out that critical angle is anywhere between 35 and 40 degrees. We actually rappelled the cables in 2 different ways. We actually would climb to the top of the tower, and then we would tie anchors off at the bottom, and then we would just let an inspector rappel freely from the top down to the bottom. Or once we got to the critical angle there, because if you can imagine a rope over 600 or 700 feet of length, there's a point where the friction of the guy coming down and then the weight of the rope hanging out on each side effectively stops the climber. And so we knew that was happening, and then you basically have to grab the cable and kind of drag yourself down, and it's absolutely exhausting. So once we found what the critical angle of the cable was, we started attaching the bags to the climbers, and we knew this was going to happen. And then that allows you to go from the top to the bottom with the rope paying out on the end, and it was much easier. But it was very difficult to get around these wind ties with these rope bags, because these rope bags, we had 800-foot lines of rope in there. It's about 100 pounds of rope. To move a climber around these wind ties, while on rope was very difficult. Don't underestimate how long it takes to bring 11,000 feet of rope up and down and up and down and up and down these towers. And let me tell you that it was 100 degrees out there with like 80 to 90% humidity. And these are a bunch of guys from, Denver, Colorado with 0% humidity. I really thought we were going to lose somebody to heat exhaustion. And so safety was paramount. After about the second day, we started working. We were on site when the sun was coming up, and we were breaking gear down by about 1 or 2 in the afternoon. Because we had to climb these towers. So inside, there's a ladder system inside each of these towers that's 310 feet from the deck where we would enter. We had to climb this, a single ladder inside these towers. Basically, we had to climb it 128 times because that's how many cables there were, and we had to bring multiple trips of gear. So we estimated that we probably climbed these towers 200 times. And so to get all of that gear up and down, this is where we didn't estimate so well. So what we ended up doing after about the second day of manually hauling gear is we actually got a motorized rope winch, and we hooked it up at the top with a bunch of pulley systems and edge control, and we started using gas-powered motorized winches to bring gear up. And then once the staff started seeing how well the motorized winches started working, and they got sick of climbing the towers, they were like, "Hey Ryan, can you motorized winch us up?" And so, sure, okay. And so then we started motorized winching people up the towers, and then our productivity really started going. But don't underestimate how long it takes to stack an 800-foot rope bag, because it takes a long time. Now, here was another lesson learned. I've been inspecting bridges for 20 years and have been on a lot of long-span bridges like this, but we really goofed up one day. They had a motorized traveler on this bridge, and MDOT was nice enough to allow us to use their traveler, all right? But what we didn't know is you had to park the traveler at the same pier all the time, because the way that the bridge was designed and the kind of the super elevation of the bridge and the vertical curve, there's that one pier where the traveler kind of set okay, and perfect. Well, we parked the traveler at the wrong pier, okay? And so then after we left the site one day, this massive thunderstorm came in, and I mean that night trees were coming down, and I mean at our hotel it sounded like a tornado was coming through, and I mean really I think the winds were that strong. So we show up in the next morning, and my crews go down and they get on top of the pier cap, and I hear on the radio, Ryan, the traveler's not here, and I was like, well, where is it? And they're like, it's out at midspan and I was like, we'll go get it. And they're like, well, how do you think we're going to go get it? And I was like, well, that's a good point there. So, we're a bunch of, rope acrobatic, we're all rope trained through the Society of Professional Rope Access Technicians. And I was like, well, look, we got 11,000 feet of rope here and a lot of smart guys. We'll figure out how to get this traveler back. So we ended up just pulling a truck up on the top of the deck right below the traveler, and rappelled off the deck right down onto the traveler, and then got it started and drove it back. But that still was about a 2-hour time period to figure out how to save the traveler. So know the equipment that you're using and know where to park it so it doesn't roll away from you. Now, this is just good bridge inspection lesson learned, or just a good lesson for all bridge inspectors. If you are going to take measurements over a long period of time, you need to have a written practice on how to take these measurements. All right, so this is a photo of when the two main spans were being connected in the center at the center line. All right, so this is the center splice here. And when they were doing, when the erectors were putting it together, they had a little fit-up issue with putting the final section in, and it created a small dip in the superstructure, and it caused all sorts of problems, and the FHWA was out there, and all these different analysis, and really what they determined is that, oh well, there's a small dip in the girder, and so you can actually see the dip in the girder right here where when they put it in. So they wanted detailed records on how to measure it year after year after year. Well, they had been doing this measurement with a string line, and so we're looking at all the old measurements, and there's a sweep measurement, there's a sway measurement to the side, and there's a dip measurement, and all these measurements, and so we get out on the traveler, and we've got this string line because that's what we had saw people do before. Well, let me tell you, if you're out there doing detailed measurements and you're trying to measure to, an eighth or a 16th of an inch on whether this center section is moving, string line is not the way to do it. And so basically, and there was no written practice, and so we really fought for a long time on, are we getting the right measurements? Are we not? And we'd pull really hard on the string line, and then the thing would break, and then we would have to go and retie it. And finally, I was like, why don't we just do this with a laser measurement, a laser magnetic level, and write a practice? And so that was one of the biggest lessons learned. There's just too much difficulty in managing that string line, and you need to have a written practice on how you're measuring all this stuff. And there were written practices for other things we had to measure. The bearings here, they had all these great details here on, this is the main spans this way and the approach spans this way, and what is the distance between this bearing and the plate. And so there was other things that had really detailed plans on how to measure, but one of the most important things, the dip in the skirter, we're measuring it with a string line. And so that was just a good lesson learned for the client to have a written practice on how to measure that stuff up. The next thing is, and this isn't anything that people haven't been doing for a long time, but when you're on rope and you're trying to do a detailed inspection of a large piece of concrete, if you have a CAD drawing in front of you, with dimensions, it's really hard to get a feel of, these piers are 120 feet wide. So when you're hanging out there and you got a CAD drawing, it's really hard to kind of see where you're at and to mark all the dimensions. And so I learned this a long time at the first company I ever worked for years ago, that sometimes taking elevation photos like this, you can reference yourself where you're at, because you can see streak lines coming down, and you can see all these form lines, and you can see where the actual bevel's at, and you can orient yourself so much better when you're taking detailed notes. And then also in the report, they look awful pretty. You can color them up and make all these sorts of legends and things. And so it just made for a nice looking report. And this is the way we decided to take our substructure notes. Now, wrapping up here, okay? I'm down, down underneath the approach spans one day, and, I'm slogging through all this muck and got my waders on and, taking some measurements and taking general photographs and this and that, and, just not paying attention. I'm down there by myself, which is probably breaking some type of safety rule while everyone is still up on the deck. And, I get done with what I'm doing, and then I go back on deck, and there were, the staff was like, did you see the alligators down there? And I was like, no. I was like, I actually didn't even know there were alligators here. I was like, I thought the alligators were in the Florida Everglades or something. I'm from the Rocky Mountains. I watch out for rattlesnakes. And so a general safety concern at this bridge is watch out near the water, because there are some big alligators down there. So next time we won't be mucking around down near the shore. So another thing is, this is one of my favorite pictures. This is Don Cressman, one of our inspectors, just loving it at the top of the towers. We had to have somebody sit at the top of the towers to monitor our anchors and use the rope winches, and just for safety and rope access safety, we had somebody up there. Well, I've already told you, it was hot up there, right? And, we asked the client, why are we doing an in-depth inspection of this bridge in the middle of July? It was brutal hot. And so the client actually agreed that the next time that they would do this in-depth inspection, they were going to move it back into May, where it's a little cooler. And so, if you're an owner that's in a area that can have inclement weather, try to adjust those NBI inspection dates to correspond with better weather, because it is hot in July at the mouth of the Mississippi River, and I am not one that does not sweat lightly, and so I was dying. I want to thank MDOT again, and KPFF, and all the consultants, and I want to thank all of you for your time here at this conference. It's been wonderful. I wish everyone safe travels, and good luck in all your engineering future. Everyone take care, and thank you so much for your time.